So just first of all, I want to make this remark that the last lecture was sketchy because I assume that you've seen this material before. Now I'm not doing this anymore. So I will go much slower and I will be much more pedantic and I will prove everything, even if you wish me not to. So, we take here, we see throughout that K is a complete so it's a field with absolute value which is complete as a metric space. Maybe it came as a completion of a more innocent field with absolute value, but we don't care about that. And we want to do geometry over such things. So we know what polynomials are, and we know what algebraic geometry is. And in order to do algebraic geometry, we don't need to assume anything analytic about K. But when you do algebraic geometry, somehow you don't have the local structure in the way when you do algebraic geometry over the reals, for example, or the complex, you get a very primitive concept of open sets and local structure, of course. And we want to ramify this. So we want to consider power series, convergent power series, not only polynomials. We want to use the completeness of K. So this is where we are after, we are going. So X, it will be very challenging this class by means of notations. So this is my warning. So X will be an interval of variables. Usually big X. And I will try to make a difference between big and small x. And
is there a difference here?
no, so far they're all coming.
They're all coming.
And F typically will be a power series. This is again big. And now alpha is a tuple. This is something in the naturals to the n. This is a multi-index. And A alpha, this is an element of K. And next to the alpha, just to make clear, I'll just rewrite it. By definition, is the product of the xi to the phi. And the summation here is over the full set of multi-indices. So this is a formal power series. And the ring of all such are then like that. Or what amount to the same. Like that. Okay, so these are the guys and stuff on the problem. Yeah, I'll write that. This is the ring of formal power series in the variable x, in the variables xi. Now, take R. R is a tuple of radii. These are n positive numbers. And PR will be, this is small x now, typically points in varieties, in sets, will be denoted by x, y, etc. These ones. So this inequality is not a norm. This is a coordinate-wise absolute value. So let me write this. So and this is a weak inequality here. So this is like a closed polydisk.
So absolute value x is by definition maximum of the absolute values, or you don't change it?
Sorry?
Do you mean that
No, I mean this is the same as.
Yeah, so what I'm asking is, do you adopt the notation that absolute value of x is equal to the maximum of the absolute values of xi?
No. R is a multi-radius,
Sorry.
and this is a polydisk. Or R is a polyradius. I don't know. This is a closed parenthesis polydisk. Of course, it might be that if I put here a strict inequality, this will be topologically closed as well, right? Because it might be that those numbers, the Ri's, the real numbers Ri are never absolute values of anything. But when I informally I think of this as a closed polydisk, and the zero here says that I'm considering an open polydisk. So this is just a notation. So definition. The power series F converges in PR, in polydisk R, if it's the bad notation. Okay. If not if you have convergence at every point, this is not what I'm defining. I want to define absolute convergence. Maybe I should have called it absolute convergence, but there will be no other convergence that I will consider. So this is what I want to do. Now, this is a series of real positive numbers. And then, so this is perfectly understood. And if we have this, for this R, we say that this is convergence. Maybe sometimes I might say that absolute value of F at R alpha is less than infinity, when absolute values of F is the real power seriously. This is a bit confusing because this is not the absolute value of F of R to the alpha, whatever. Okay. Oh, sorry. This is a short annotation. And F will say that it is converges in question? Converges in the open polydisk if for every S smaller than R, and converges. Here I'm writing something very stupid. You should agree with this, eh? This is a trigger part of what I want to write. M here could be taken that sum, for example. And of course, M is bigger than every term in sum. And if you have this, so this is an independent implication now. If you have this condition, then you can conclude that F converges in, this is also easy, and basically you should know the proof, but this is what I wanted to emphasize. F converges in P0. Let me put this proof for you. But you've seen this in complex analysis or something. So, I'm doing this implication. And I'm taking some S, which is smaller than R. I'm not writing down the rows. And I'm assuming that for some specific M, of course, and I want to show convergence, actual convergence in the closed PS. So I want to look at this guy. You remember what do we mean by this?
Yeah.
So the S alpha is the product of Si to the alpha i's, just reminding. Okay. So let me rewrite it. There's no and now each of these guy is bounded by n. This is my assumption. So I can take this majorization by n and take it out of the sum, and now I get okay. This is geometric series. You have here it's multi-dimensional one, but just figure yourself. This is I of y minus si inverse. Or what? Which I guess I should say is less than infinity. And maybe what I didn't explain explicitly is what this symbol means, but probably you got it. This, not this out. This means that for every I, Si is strictly smaller than R. Right? This means this is some maybe small number, not 0, and its inverse is maybe big number, but not anything. Okay. Yes.
Either multiplication to the new direct product or a natural multiplication of the coordinates.
This is coordinate-wise multiplication. This
No, that's true, but is it a one number or an interval again? Because
no, this is a number.
so
I mean, again, everything here is a number. S itself is not a number, but S to the alpha is a number. S to the alpha, and you should substitute Si to the alpha I. Each piece like that. You miss that. So somewhere, at some point, I hope I did write it down. Okay, excellent.
No,
So I should have written it down.
You written it there.
No, this is about X. No, this is a legitimate. I think it should be well, alpha is okay. You could figure it by this notation, which also appeared the definition. Sorry for that. So let me pause and read it again from here. I guess that the convergence of F means that this thing convergence. This is an infinite sum of positive numbers. When I need to understand these are numbers, this guy is a real number. This we know. This is the absolute value of something. Okay, which goes to the reals. And this expression is a product of real numbers. It's given by that, and I would use this again. Kind of notation over and over again until we get sick of that. This is part of our game here. And so we understand this definition once we understood that one, we understand this definition again, and okay, it is now power line. Important corollary. If our field is non-Archimedean, and if all the coefficients here, all the a's, are of absolute value less than 1, then what can you say about that? Then I want to assume that I want to reduce it to convergence in some quantities. So I want to have this for some R and some M. Which R can I take? 1. Excellent. If I take R to be 1, I can take M to be 1, and this is satisfied, and I have convergence. So I have a huge bunch of formal power series which converge in a big polydisk easily. F converges in T0, 1. Which this is, I guess I should write it like that. But when I would just put one real number, this is what I need. So the analytic theory is not so bad. We do have convergence easily, at least for periodic fields. So for real and complex numbers, we have some feeling already of what convergence means, and we know a little bit about it. So I guess that the new input of my lecture now is to be cool about it also for the periodics and other non-Archimedean fields. By Stokes' theorem, right? These are the only things that left. And we can do this.
So, in the examples we know, we usually talk about convergence, not absolute convergence, right? So what will
Well,
happen?
usually, when you have convergence in some disk, you have absolute convergence in every smaller disk, right?
Okay.
Absolute and uniform convergence.
But what will happen if we talk about it in general?
So I don't want to.
Oh.
No, you say for complex numbers, just assuming convergence, you already get convergence in smaller arrays, right? Okay. The truth is that I don't really know. I didn't think about it myself enough. And I assume that, I mean,
I think in the periodic numbers this will always converge.
sorry?
I think in the periodic numbers this will always converge, even not absolutely. coefficients are
So I don't know.
I think you can, the corollary you can say that even without absolute convergence. But never mind.
What do you mean? I deduce absolute convergence, which is stronger than convergence.
I think he's referring to the fact
Yeah,
that
okay.
over the p-adics, if you know that the main term goes to zero, then the series is actually absolutely convergent automatically.
Yes.
So that's what.
Now again.
Okay, so just a minute. So I got absolute convergence, which is stronger than convergence. Maybe I should. I didn't make this remark yet, but
Did I get you
here it
correctly?
is. So I guess.
Yeah, in this case, there's nothing to say.
Then, Max, if anything, maybe this is what you want me to say. F convergence qualities implies. So you have a priori, I mean here that I have absolute convergence in smaller disks, closed smaller disks, and what I do actually get is convergence at each point. Whenever, not of the real functions that I get by absolute values, but the actual series, if I substitute the actual points in the disk, I will get an actual convergence in the field. F defines well, moreover, a continuous function by now this is little x, right? And this x to the alpha, I need to understand it as x product of xi to the alpha I. And this is some infinite sum, is not a priori defined, but absolute convergence says that it's finite subsums actually converge in the topology of K. So this is an element for every x, and for every finite sum, I'll get an element of K, which is a topological space, a metric space. So I'm getting here a sequence. Well, it's not a sequence, but since I linearly order the
partial sums.
but I can take partial sums, and actually, again, by absolute convergence, order of summation, I want to make this remark as well. Summation makes no difference. So this is the standard theorem that you know from real analysis or complex analysis. If you have absolute convergence, of order of summation does not matter. This is the case here. I don't want to discuss conditional non-absolute convergence at all, because I don't want to fall into those traps. I will always assume absolute convergence in the field. So by absolute convergence, again, this point-wise, for every x, this makes sense and you have convergence. Moreover, now if I shrink a bit, for every given x, actually sit in some closed polydisk for some smaller s, right? So when I discuss this, I can always assume my polydisks are actually closed, and I can always assume that this thing actually is actually finite. This I did this to argue for convergence here, and but not only it is finite, this is uniform. Somehow the convergence is the same as similar rates for all x's in that polydisk. This means, I mean, that if I chop, if I'm just looking at the tail of this infinite sum, if I chop a big enough finite subsum from it, I can evaluate the rest by means of the tail of this real sum, real series, and this will be uniformly bounded, right? So I have this function here that I'm getting is uniformly approximated by polynomials. So if you give me some epsilon, maybe up to a third epsilon, I can cut a polynomial part of this, which gives an epsilon third approximation at every point in this closed polydisk. And this polynomial now is continuous, I know that. So if I have a point close to x, y, close enough, for some delta, the values that I will get will be epsilon third close again. So by adding 3 epsilon thirds, I will get that the value of this sum at x and the value of this sum at y for that delta will be epsilon apart. Okay, so this is the proof of continuity. Okay, so I prove it. Okay, fair? So I think I have this theorem out, right? Okay. So absolute convergence is what I need, or what I want to assume in order to actually get functions from power series at those closed points. Now, so here's another lemma. I can look at f such that f convergence, and of course by my notation f, you see that I'm thinking of those things as functions. But usually when f here will always means, I'm not writing it down precisely here. It is a formal power series. But now I'm looking at those who do converge in this polydisk. And I got a map which I will not use another symbol to the function f. This is a continuous function on the same domain. And the lemma claim this is injected. So let's examine just for a minute the properties of this of this plane, of this map, of spaces. So this is a linear subspace of the ring of polynomial of power series. And this is of course a vector space as well, a vector space. And so this is obviously a linear map, and the claim is that its kernel is 0. So I want to show that if a power series as a function gives me the 0 function, it must be the 0 power series. But I will do it anyway. I'll do it by induction on dimension. Should I stop and continue 1 hour?
5 minutes. 3, 5 minutes. 4 ו-17.
כן, 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 אני לא אעצור עכשיו, אבל השאלה אם זה ברצף או לא. כי נראה לי שמי שיתנגד עליו. Okay, for n equals 1, again, n is a dimension, remember? Yes, please.
I have a stupid question. So, even the fact that you land in a space of continuous functions, this follows from what you did about geometric series.
This is this lemma. No.
I mean, the fact that you
This
get
lemma, I didn't write down a proof, I already said it. I explained this lemma. And this lemma says that, so there was an epsilon third argument using uniformity of the convergence. Okay, so this is standard.
okay, so
No, I didn't use this. I made this basically not to make this lemma.
So my question is, suppose you have something that converges in the closed thing, okay? Do you know that it need not be continuous on the boundary, right? Or
No, it need not
need
a priori continuous on the boundary. Yes.
You don't have an apples.
Frankly, I don't know. It's very easy to ask questions, but I don't know it. I didn't spend much time thinking about just this theory, so I'm not sure what happens on the boundary. I mean, if you have absolute convergence, if you converge in PR, not P0R, same argument holds. You have continuity on the boundary. If you have conditional convergence of some sort on the boundary, I don't know what to say. I think no, I don't think this is the case. Okay, maybe maybe I
No,
don't.
I don't. In any way, we're only considering absolute convergence.
I only yes. I insist. Okay. I mean, our purpose is to develop as simple theory as possible that we can use and it helps. Of course, once you have a theory, you ask further questions and you want to extend it, but at this point, we don't have much motivation to explore the boundaries of this theory. I mean, at least myself. I want to develop the theory that actually can be used in the simplest fashion. Maybe this wasn't the where am I? Yes. N equals 1. So I'm assuming I'm assuming all those fancy notation are just honest to God, a number to the power of a number, etc. I have only variables, not multivariables, and I want to prove the injectivity here. So f could always be written as x to the k times something like that. Right? Take the first term, which is not 0. Now k is a natural number. This is the alpha of mine. I mean, the indices are natural numbers. So take the first indices, which is not 0, and just, in this case, the order of 0 of this function f. And we call this guy g. G at 0 is ck, which is not 0. G is continuous. Hence, G as non-zero in a neighborhood of the point 0. Xk is 0 only at 0. And so the product of them is never 0. So f non-zero in a neighborhood. In a function.
Why does G converge?
Exercise. But okay, if you want, if maybe get convergence on some smaller. But actually, it converges on the same. I mean, just do the summation. Okay, so this is the case n equals 1. Now, so let me write f as a form a power series in the last variable. So so I is a natural here, and I can always write it like that. These are formal power series. Just organizing things. And again, I'm using, without mentioning all along, that I can reorganize terms in sums. And also, I'm using, I'm leaving it for us to observe that those guys, all the CIs are formal power series, and they do converge in, well, in the corresponding polydisk. So the polydisk, I guess, so I'm leaving it to you to read like that. Now, the case n equals 1. Now, if you find if you substitute values for the first xi's, whatever values, we get the case equal 1 power series, and which will be converging, and it will give us. Okay, this f, I'm not writing it down formally. I'm assuming that it is in the kernel of this part. It's a formal power series which gives us the zero function. And what we conclude that this f, or this formal power series here, is the zero formal power series, which means that all the coefficients which means all the coefficients, for whatever value substitutions, are zero. They're zero as functions by induction. That's induction. Was I clear? Okay. So I think it will be fair to stop here. Just a minute. אופיר, השעון החוגים מראה לי בחצי והשעון הדיגיטלי מראה לי 25.
תבחר מה שיותר טוב.
So let me give some definitions and then.
טוב, 7 דקות אוברטיים זה לא...
אוקיי, בסדר. זה אוברטיים, לא חשבתי. טוב, אז נתראה עוד שעה.